All right, so our next talk of the morning then is Eric Evert, who's going to talk to us about tensor decompositions of positive definite tensors. So go ahead.
Okay, thank you for putting this together quite last minute. It's nice to have some replacement to the JMM, and also thanks for letting me speak some. I'll mention that this is, well, not exactly operator theory, but I did come up in operator theory, and a lot of the ideas that I've been thinking about these problems with are very informed by my operator theory upbringing. So I hope you find it interesting. I certainly think there's a lot of nice math in the tensors world. Okay, so I'm going to try and give a careful introduction to the subject, knowing that this is not the expertise of the audience, and also knowing that one of the most challenging things about tensors is just quite frankly getting used to some of the indexing notation. And due to the results I want to present, I have to work in the arbitrary order case rather than the order 3 case. So yeah. So for me, a tensor is just going to be a multi-index array of size, say, I1 by I2 by up to In. So you're just thinking of sort of a n-dimensional generalization of a matrix. And you say that the order of your tensor is n. Now for the talk, I'm going to take all these indices to be the same size. So, I'm thinking of an I by I by I array, for example. I'm going to denote that space with Ri, tensor with itself, and times. So it's nice to have examples. A 2 by 2 by 2 example you can write down very nicely is defining the tensor T entry-wise. The ijk entry will be I plus j plus k. So for example, if you want to know what the 1, 2, 2 entry is, you put a 1 and a 2 here. You're looking at the first row, second column, second slice of the tensor, and then 1 plus 2 is, of course, 5. Now, these tensors get big quickly, as you can imagine, so it's not very practical to write down tensors by specifying all their entries. Instead, what you want to do is typically use a tensor product, which I'm going to identify with the outer product. So if you have vectors, say v1, v2, up to v capital N in your I-dimensional space, which I'll denote by v subscript n, its first entry is denoted by parenthesis 1, second entry parenthesis 2, and so on. Then this tensor v1, tensor v2, tensored up to vn, which is living in this I by I by I by I space, has I sub 1, I sub 2, up to I sub n entry equal to basically the product of the entries of these vectors, where the nth index specifies which entry of the nth vector you're multiplying in that product. Okay, so if you look at the n equals 2 or the matrix case, then this is just the outer product between vectors. So if you look at the product between vectors A and B, then the tensor product of A with B is equal to A times B transpose, which certainly has ij entry equal to ai times bj. Okay, so these are special tensors in the sense that the linear span of these tensors gives you the full space of tensors of whatever size you're looking at. And since they're special, we call them rank 1 tensors. Okay, so as I mentioned, every tensor can certainly be expressed as a sum of these rank 1 tensors. It's very easy to do if you want an inefficient representation. You can just specify the ijk entry of your tensor, and you can, for example, multiply that by ei tensor ej, tensor ek, where these are standard basis vectors. So this ei tensor ej, tensor ek is a tensor where all entries are 0 except for the ijk, which is 1. So you're really just specifying the entries of T here. This isn't at all a minimal decomposition, though. If you want a minimal decomposition, you're interested in what's called the canonical polyatomic decomposition. I like to call it the tensor rank decomposition, because it's a simpler name. And you just are writing T as the summation from R being 1 to L of V subscript 1 superscript R tensor V subscript 2 superscript R up to V subscript N superscript R. So the subscripts are denoting what mode the tensor or the vector is being tensored in, and the superscripts are denoting sort of which summand the vector belongs to. And then if L is as small as possible, you say that that's the rank of your tensor. Okay. So, and if you like pictures, you can imagine that you're taking this vector and you're multiplying each entry by this vector, and then you're multiplying those slices you get by this vector, and you sum those up and you get a full tensor. So this certainly generalizes matrix rank, tensors being generalizations of matrices. This should be the case. If you have a matrix M, you can write, for example, its truncated singular value decomposition. You can let A be U times sigma, and you can let AR denote the rth column of A, and you can let VR denote the rth column of V. Then what happens is M is equal to A times V transpose, which if you just write things out is equal to AR tensor VR, the sum of that. But it turns out that the tensor rank problem is really a lot more interesting than matrix rank for at least 3 reasons. There's actually more that I don't have time to go into. But first off, sort of the expected rank, being loose what I mean by expected, of a tensor in this space here, first off, is much larger than I. So that's really very different from the matrix rank setting. Another important difference, which is really important for applications, which I won't have too much time to say anything about, but you can trust me on that, is that if you have a low rank tensor which satisfies very light assumptions, then the canonical polyadic decomposition is going to be unique. Compared to matrices, basically any matrix decomposition, you can insert an invertible matrix times its inverse in the center of that matrix decomposition. You get a new equivalent matrix decomposition, and you have no notion of uniqueness there, unless you impose, say, orthogonality as you do in the singular value decomposition. But then another thing, and the focus of my work, is the fact that tensor rank is not lower semi-continuous, which, for example, means that there's a sequence of rank 2 tensors which converges to a rank 3 tensor, or stated alternatively, the set of tensors of rank less than or equal to R is not closed unless either R is equal to 1, or if R is sufficiently large. Sufficiently large meaning that R is basically the largest possible rank of tensors of that size, and then it's trivially closed. So I'm going to say a little bit more about this point and this point. First about the expected rank, because I think it helps you sort of think about tensors, because it's essentially just a simple counting argument that tells you this. So it turns out that the expected rank of a tensor of this size is just about equal to I to the n-1th power divided by n. And certainly if n is larger than 2, that's going to be very big very quickly. And the simple counting argument is really just count the number of entries in a tensor. So, a tensor is going to have I to the n entries if it's I by I by I by I. And then count the number of entries, sort of the maximum number of entries that a rank 1 term can specify. Well, in each of these rank 1 terms, you have n vectors of length I, so you get to specify n times I terms. And you need to specify a total of in terms, so that's where you get this I to the n divided by ni from. That's exactly this. Okay. So hopefully that helps you start thinking about tensors, because now we'll move to sort of the more exciting thing, in my opinion, of the fact that tensor ranks not lower semi-continuous. So first I'll give an example, which is this tensor here. It's a famous example of a rank 3 tensor, which is a limit of rank 2 tensors. And the way you write this thing as the limit of rank 2 tensors is you write S as the limit as n goes to infinity of minus n times E1 tensored with itself 3 times, plus n times E1, plus some small perturbation tensored with itself 3 times. And if you want to see what that tensor looks like as n goes out to infinity, it's written here as a tuple on the slide. So one of the things that's so sort of strange about this phenomena is that what you see happening is this first term is essentially approaching having infinite magnitude as n goes to infinity. And the second term is also approaching having infinite magnitude and is essentially approaching being anti-parallel to the first term. So sort of intuitively, the way that I think about it is your tensor S is sort of being expressed as the limit of some destructive interference between these two signal tensors, which roughly have infinite magnitude. And of course, if you do want to relate to applications, that's very unsettling because your application shouldn't have infinite magnitude signals in it. And it's also just mathematically interesting, I think. If you think about it for a bit, you'll realize that this is essentially what has to occur whenever you have this phenomena, because if these tensors didn't have magnitude going to infinity, then just by some simple compactness argument, they would converge on a subsequence, and then you would be able to get some same rank expression for your tensor. So this is really a phenomena that always occurs when you have this problem. Now, in general, you say that a tensor has border rank 2 if it's a limit of rank 2 tensors, or border rank R if it's a limit of rank R tensors. Okay, so this is something that I think seems really strange when you first encounter it, but it's actually very simple if you have the right picture for the geometry of the set of rank 1 tensors in your head. So in a toy example here, I'm going to identify the set of rank 1 tensors with this blue curve here, and I'm going to pretend that the set of 2 by 2 by 2 tensors is this 2D plane. So what it means to be rank 2, for example, is precisely that you're a linear combination of 2 rank 1 tensors, or that you're on the line between 2 rank 1 tensors. So for example, this point S0 here is rank 2 because it's on the line between P0 and R0. Now, if you look at this point X, there's sort of this horizontal, well, in fact, there is this horizontal asymptote, which the set of rank 1 tensors is approaching. And due to that horizontal asymptote, the point X is not on a line between 2 rank 1 tensors. However, I can sort of let P0 go off to minus infinity and R0 go off towards positive infinity, and the midpoint will then approach X. And sure enough, if this plays, yeah, you can see that the midpoint is indeed approaching X. So this really captures the behavior that we saw in those rank 1 terms on the previous slide. And this is the picture that you should have in your head for this phenomena. As it turns out, it's actually sort of the expected behavior. If you write down some algebraic curve that is your set of rank 1 tensors, you expect to have points like this. It's actually somewhat of a miracle that matrix rank doesn't exhibit this phenomena. Okay. So let's see how, okay. I have time to say a little bit about why you might care about this in applications, which is roughly that, so as I mentioned previously, the uniqueness of low-rank canonical polyadic decompositions does indeed make CPD a really big tool in applications. And the reason for that is often you have some signal or data set or something of the sort, which you imagine as being some low-rank tensor, or for physical reasons, maybe you know it is well modeled by some low-rank tensor. And the idea is that by decomposing this signal, you can reveal component information, which gave you the measured tensor. So a big example of this is blind source separation, where pretty much exactly as I just said, you have some mixture of sources and you want to extract out these sources which are responsible for the mixture. A more concrete example of this blind source separation problem, my favorite example of it at least, is you have lots of groups of people in a room. They're all having conversations. You place a bunch of speakers around the room or microphones around the room to record the conversation. Each microphone gets in sort of a garbled mess that can be represented with as a matrix with a time axis and a frequency axis. And then you can stack those matrices together in a tensor. And you're thinking that this tensor should have a low rank decomposition because there's only so many conversations in the room, and each of those should sort of be one component of the tensor. And then due to the fact that the decomposition should be unique, if you can successfully decompose the tensor, you get out a you get out the conversations themselves. But there's a big problem with this whole setup, which is that, of course, when you're working in the real world, you're going to have noise on your measurements. So your tensor that you get is not actually going to be low rank. And you need to, in order to do anything, first compute a low rank approximation of the tensor. But since, say you want to compute a rank 2 approximation, well, since the set of rank 2 tensors isn't closed, maybe your best approximation is one of these things, which is rank 3, but a limit of rank 2 tensors. And then if that occurs, well, your signals that you get out are these infinite magnitude things, which are expressing destructive interference to get out your tensor, and that's totally nonsensical for what you want to do. So you want to know that this type of problem doesn't occur. Essentially, you want to have guarantees for existence of best low rank approximations of tensors. Okay, so I will now tell you how we got a deterministic existence guarantee for best low rank approximations for these positive definite tensors. And first, of course, I'll tell you what a positive definite tensor is. So I'm going to say that a tensor is symmetric simply if it's invariant under a permutation of indices. So more precisely, if you have a permutation pi, which acts on 1 to capital N, and you shuffle the indices of your tensor according to that permutation, then the tensor needs to remain unchanged. So for example, this border rank 2, rank 3 tensor that I showed you previously is indeed symmetric. To tell you what I mean by positive, I need the inner product, which is just the Frobenius inner product. You take the sum of the entry-wise products of your tensors, and that's your inner product. This is the same as if you just flatten out the tensors into vectors and then take the inner product on the induced vector space. It's the same inner product. So it's very natural. And then we say that a tensor is positive definite if its inner product against a non-zero vector tensor with itself n times is always positive. This is a totally natural generalization of positivity for matrices or positive definiteness for matrices, where the inner product of T with X tensor X is exactly equal to X transpose times T times X if you're in the order 2 case. Okay, so a useful piece of notation will be this lambda min of T, which is the minimum of the inner product of T against unit vectors. In the case, I'm not requiring T to be symmetric to define this quantity, but T is positive definite if and only if this quantity is positive and T is symmetric. And then in the case that T is symmetric, this really is a meaningful notion of an eigenvalue of T, but I won't go into that. Now, a note which may or may not be clear is that for a tensor to be positive definite, you certainly need n to be even. And that's because you can factor constants out of your tensor product according to the power n here. So T tensor with minus v, T inner product minus v tensor with itself n times. I guess the parenthesis is in the wrong spot there, but that's okay, is minus 1 to the n times T inner product v tensor with itself n times. Okay. So then the first result that we have is just a nice statement about the geometry of these positive definite tensors, which is that the set of tensors of rank I is relatively closed as a subset of the set of positive definite tensors of this size. So in other words, if you have some sequence of tensors Tj, which are all positive definite in rank I, then and they converge to some positive definite tensor T, then T has rank I. And then, just one more way to say that is that if T is positive definite and has border rank less than or equal to I, then T in fact has to have rank equal to I. Okay, so since we pretty much know when the set of, we have some condition which guarantees that our tensors are closed with respect to that condition, in order to guarantee existence of best low rank approximations, all we need to do is guarantee that this condition holds. So to introduce the bound, I need to tell you what the tensor spectral norm is, which is a very natural generalization of the matrix spectral norm. You just take the maximum inner product of your tensor T against rank 1 tensors V1, tensor V2, tensored up to Vn, subject to the Vn all being unit vectors. And then what the result is that if you have tensors T and N, you assume T is symmetric and has rank I, N is just arbitrary noise, not necessarily symmetric. If the spectral norm of T is less than the minimum eigenvalue of T plus N, then your tensor T plus N has a best rank I approximation in the spectral norm among symmetric tensors. So this is nice, I think, because there are a lot of applications, in fact, where your tensors sort of arise due to some statistical information. Your tensor could be, say, a covariance matrix or a fourth moment or something like this. And these tensors should indeed be positive definite because of the way they arise. So roughly what this is saying is that so long as your noise is small enough that the tensor that you measure is going to be positive definite, you can get a meaningful best rank I approximation. So if the measurement makes sense, the problem makes sense, and that's good. I had some things written about the proof because it's a reasonably simple proof where you're essentially just doing some triangle inequalities and expanding out what the spectral norm means in order to verify that the best border rank approximation is positive definite, thereby being the rank you want. But I'm not going to go into that because I think, well, I'm close to the end of time. It's probably better to leave time for questions and break. I have these graphs of what the bound looks like. You can generalize these results to work in the odd order case where you're looking for a linear combination of frontal slices, which is positive definite rather than just a positive definite tensor. It's just a little bit more complicated to state and not so great for the sake of the talk. But if you do that, you can actually compute the bounds with semi-definite programming, and you can see that you get some nice bounds compared to a perturbation theoretic method for getting existence bounds. Anyways, thanks for your attention. I hope it was interesting. And that's it.